When we look at position versus time data, we've essentially seen two different types of graphs. We've seen constant velocity motion, and we know that the velocity on a position time graph is the slope, or how fast your position changes. And we can see that for some motions, that slope is constant. Those are objects going at constant speed. Objects that are speeding up, like this one though, their slope is not constant. It gets steeper and steeper and steeper. And that corresponds to a larger and larger velocity. Here's a graph of an object slowing down. Its slope is getting shallower and shallower and shallower. So we started to look at another type of graph called a velocity time graph. And this is some lab data from a lab I did several years ago. And here's my position time graph. As you can see, it's showing speeding up as the slope is increasing. And we can also graph that slope, that velocity, at every single time and generate what's called a velocity time graph. So this velocity time graph shows the same idea. Because the velocity is increasing, this thing's getting faster. And I actually generated this graph by taking the slope here and here and here and here, and then plotting those slopes. So if slope is so important, if the rate of change of position corresponds to velocity, we look at this graph, it's clear we could take its slope as well. What does the rate of change of velocity correspond to? How quickly your velocity gets faster. Well, that's a new concept called acceleration. And acceleration is the change in velocity divided by the change in time. And that's just equal to the slope on a velocity time graph. It's how fast you get faster. And that's really the point of this video. We're going to take a look at how you make an object change its velocity. And we'll see if we can get any insights from this motion. Our overall goal is going to be to get some sort of equation that describes motion that has acceleration in it. So let's look at some data of some object accelerating. And that object is going to be my colleague, Mr. Nazaro. All right, so I have a spring scale, and I'm going to pull Mr. Nazaro with a constant force of 10 pounds. So the question has to arise, what causes acceleration? And the answer is unbalanced forces. Now we'll look at forces a ton later. It's a major topic of this year. This lab's really focused on the acceleration part. But forces are things that push or pull people. And there was a fair number of things pushing or pulling the rider in this lab. So there's the spring scale that I'm pulling with. There's the ground pushing them up. There's the Earth's gravity pulling them down. There's a little friction pulling them back. But these were not balanced, and that made the rider get faster and faster and faster. So let's go to Tracker and plug this data in, and we'll see how Mr. Nazaro accelerates. One other thing worth mentioning. All of the forces on Mr. Nazaro here are constant. I took really good care with that spring scale to make sure the force didn't change. So this analysis is going to be limited to constant forces, which are the kind we're going to study most this year. All right, so I'm going to use the wheel of the cart as the thing I tag, and we'll see what our position time graph looks like with this unbalanced force on Mr. Nazaro. We get going pretty fast by the end. We actually nearly ran down an English teacher. So you can see he's going farther and farther in each successive frame. And that's another way of saying the same thing that that position time graph is saying. All right, so there's our position time graph. Notice that the dots on here are spreading out. This is a location in each of the last few frames he was in. And that's another way of showing that he's getting faster and faster. Basically, in each time period, he covers more and more distance. So what we can do is we can have Tracker get us an equation for this motion. So the way we do that is we go up to View, Data Tool, and we're going to go to Analyze, Curve Fits. So clearly it's not a line, but what else could it be? Well, we have some options, and for me that looks the most like a parabola. And we can see that the parabolic curve fits it very, very, very well. So it gives the equation in the form of a times t to the squared, b times t plus c. And then it gives you a, b, and c. So let's write that in a slightly easier to read way. So that's the equation written out more reasonably. And we can see that it depends on time squared, it being a parabola, but also time. And these numbers actually have some very specific meanings on this graph. And let's take a look at what they are. So I think the easiest way to figure out what these numbers might mean is to take a look at the units of time. So I have this picture here, which is from a different lab, and I apologize, I'm using Y for position. It was for an up and down motion. But I've got that same t squared and t and then term without t. Since the unit of t is seconds, that means the unit of t squared is seconds squared, and the unit of t is seconds. Since all of this is adding up to a position where you are, that means that the units have to cancel into meters, because you can't add meters to seconds to meters per second. Every one of these terms at the end of the day has to be meters. So it's pretty simple for the last term. That must already be in meters. So this last term must be a position. And it turns out it's the original position. This second term, to get rid of the seconds, I need to multiply by meters per second to get a meters. So this must be a velocity times a time. And it turns out it is. The velocity in question here is the velocity you start with, the original velocity. Lastly, I've got this t squared term, and that means the unit that I have to cancel with is meters per second squared. And meters per second squared, it turns out, is our new acceleration term. And let me show you why. When you calculate an acceleration, you're doing the change in velocity over the change in time. So you end up with meters per second. And we abbreviate that as meters per second squared. It's kind of a strange thing, but whenever you see that meter per second squared, we're talking about how fast we get faster, the acceleration. So ultimately, this becomes our equation that we can use for constant acceleration motion, like the kind you saw here with me pulling Mr. Nazaro. Position equals 1/2 at squared plus VOT plus YO. I can't really justify where the half comes from. You'll learn when you take calculus. But we can use this equation for any sort of constant acceleration motion. All right, so our equation that we're looking at now can tell us about the motion where I pulled Nazaro. We can see that the numbers for initial velocity and initial position are very low. And that's because we basically started him from rest. and I called the place we started from the 0 point. So those are essentially 0. The 0.377 tells us about our acceleration. And because of this weird quirk of the equation, it's not the acceleration, it's only half of it. So our acceleration in this case was actually twice that. So 0.75 meters per second squared. So now we have an equation for constant acceleration motion. This depends on the fact I pulled him with a constant force. And we can use this equation to relate time to position. Now, it would also be nice if we could relate time to velocity. And it turns out there is a simple way to do that. Just like we generated our velocity time graph by taking the slope at every single point along this parabola and came up with the velocity time graph, we could get the slope of this line on the velocity time graph. And because it's a line, it has the formula y equals mx plus b. And if we customize y equals mx plus b for a velocity time graph rather than a position time graph, we end up with this. On the y-axis, we have velocity. The slope on a velocity time graph is acceleration. On the x-axis, we have time. And the intercept would be just whatever your speed you're going at the beginning. So this equation could be used to figure out the relationship between time and velocity. Taken together, we have two powerful equations that help us find out about a lot of physics variables with accelerated motion. Okay, so here's our two equations that we just got. They're often written with a third one, which is closely related. And if you look, it's been solved so that there's no t in it. And that makes this one the best one for relating positions and times. This one the best one for relating velocities and times. And then this one, we've eliminated time, so it just relates velocities and positions. So taken together, those solve lots of different physics problems. We also have our original equation we learned in the first very simple walking lab. And notice that that one lacks any information about acceleration. So these are different models. This is the one you use when you have constant velocity. It's part of our model for constant velocity. If you have constant acceleration, these are the ones that you use. If you don't have a constant acceleration, if something's speeding up or slowing down a bunch in a kind of a random pattern, we don't have a model yet that works with that. So those are the equations we've learned so far, and now we need to learn how to make use of them.